So thank you all for joining today. I'm David Anderson. I'm the training coordinator at Ververica. One of the questions I've been getting quite frequently in the training sessions I do with our users is asking for help getting started with using Apache Flink on Kubernetes. So I've chosen that topic for today's webinar. So just a quick introduction to who we are. Ververica is the company that used to be known as Data Artisans. We are the creators of Apache Flink and also Ververica Platform, which is a real-time stream processing platform for the enterprise. I should mention that we are recording this session and we will be sharing it online, I guess by tomorrow. So here's an outline of what I'm going to be presenting. First, an introduction to the topic. Then I'm going to go through a detailed example. I'll give some debugging tips and close with some information about future plans. I'll address questions at the end of each of these sections. So to begin, why is it interesting to use containers for Flink? Well, these are the reasons really that apply to using containerized infrastructure in any setting. And it all boils down to saving money. Containers provide isolation at lower cost because they're more efficient, use resources more effectively than other techniques for virtualization. Containers are smaller, they boot faster. They're also simpler to manage. Each container does just one thing, so you have a nice clean separation of concerns. And just like you see in the Docker logo, with the revolution that it came to the shipping industry with having containers there, where you have consistent packaging and you can transport containers by ships and trains and trucks. The same basic idea applies here, where containerized infrastructures for IT allow for consistent deployment and portability. Also makes things easy to scale. If you have pieces that each do one thing, you can replicate each piece according to your needs. And you can compose the containers together very conveniently and to build many different things out of them over time. Now, in addition to having containers, you also need some way to manage the fleet of containers you end up with, and that's what Kubernetes is designed to solve that problem. It works in a declarative fashion where you describe what you want to have running, and a set of background controllers makes that happen. So for example, you might say that you want to have 3 replicas of a specific container running at all times, or that you might want to have a load balancer backed by a certain container that's open on port 443. Now there's a set of specific objects or resources that Kubernetes is designed to provide, and the ones I've listed here are the ones that I'm going to show in the example later. So a pod is simply a group of, in the example, it's just going to be each pod is going to have one container, but conceptually they can have multiple containers. A pod is just something that runs and might die. It's just a piece of virtualized infrastructure. The job abstraction is layered around a pod, and it keeps a pod running until it's finished. So if the pod fails in some way, the pod will be restarted as needed until the job has run to completion. Deployment is similar to that in that it's an abstraction that also keeps some pods running. But here the idea is the deployment is meant to be running indefinitely, and it's meant to be a scalable thing where you've got a fleet of these pods that you can scale up and down as needed, and they're just running continuously. A service lets you wrap a REST service around either a job or a deployment. And you can expose ports internally to the rest of the cluster or externally so that you're exporting a REST service from your infrastructure. And then finally, we're going to need to have persistent volume claims. This is how you have storage in Kubernetes where the lifetime of the storage isn't coupled to any one of the pods. You want storage that outlives the pods that might use the storage. So that was probably review for many of you. And this might be too. But what I want to talk about here is a little bit about Flink's runtime, because we're going to talk about how we then map this onto Kubernetes in just a moment. So over the past year or so, during a process we called Flip 6, which is a Flink improvement proposal, the Flink runtime was significantly refactored, and what we had traditionally known as the job manager was refactored into these three pieces that are shown in the highlighted section here. The new job manager is a much simpler thing that manages exactly one job. It's responsible for scheduling the pieces of the job into task slots, and it monitors the ongoing running of the job. The dispatcher is where you submit your job to the dispatcher and it creates job managers. And the resource manager is the piece that's cluster framework specific. So we'll be talking about the need for a Kubernetes specific resource manager that is able to acquire and release resources from Kubernetes and to create and destroy task managers as needed. This is the piece, as we'll see in a minute, that's actually missing in Kubernetes so far. Now here's how those pieces I just described map onto Yarn, where the story is fully available at this point. So you have your Flink application that's running. It submits a job to the dispatcher. It starts a job manager. The job manager requests resources from Yarn, in this case. The resource manager starts up task managers as needed. They present their slots to the job manager, and the pieces of the job get deployed into the task managers. That all works nicely, but we're not quite there yet with Kubernetes. So the situation with Kubernetes is currently that Flink is really not aware at all of Kubernetes. So in this environment, we're really only establishing a very static execution environment. So as you'll see in a couple of minutes, we're going to have a Kubernetes manifest that effectively says there should be some number of task managers that look just like this. Those are the resources that exist. Please make use of them. We won't be able to more dynamically operate at this point than that. So that ends up looking like this, where we have two container types. On the left, you see the master container. This is running what's effectively the job manager. And then we have a fleet of worker containers, each running a task manager. So with that introduction, now I want to go through an example in some detail. Just checking to see if there are any questions. Okay. So for this example, I've established a very simple streaming job. You can see the URL onto GitHub where I've shared this example. I'll share this URL again later at the end of the talk if you don't have a chance to capture it right now. What this job is doing is there's a simple data generator that's generating events about users. These streams are keyed by the user ID, and in a rich flat map, it's counting the number of events for each user, and whenever that number becomes 0 mod 500, so every 500 events, it generates a little report that gets printed. And here in this little video, we can watch this running in my IDE, so you can see Flink is starting up. And then after a moment, when it gets running, it'll start producing these little reports about what's going on. So we can see each of the user IDs and that the count of events is going up. That's really all this job does. I chose this so that so that I could easily see, for example, when the job, if I caused it to fail and restart, or if I scaled it up, I just wanted to be able to see that the state was being maintained. So I wanted to see these counts keep going up and not reset back to 0. That was really all I cared about. So this is the landscape that I want to build for this in Kubernetes. You can see that on the right, I've got a scalable set of task manager pods so that those are wrapped in a task manager deployment. On the left, I have a job cluster service wrapped around job cluster pod. So this is running the job manager. It's exposing a set of ports that you see on the right that the task managers can use. And it's exposing a set of ports on the left to the outside world so that we can manipulate this job from outside the cluster. I'm also going to establish a Minio service inside here that I can use for checkpointing and safe pointing and for bulk storage for high availability. As part of that Minio pod, so Minio is an S3 compatible file system. As part of that, there's a little job here called the Minio setup job. That's just living long enough to create the buckets that we want to have in Minio, and then it goes away. You'll also see that there's a persistent volume claim here because I want these checkpoints to be durable. So I'm going to describe the setup of this job in 4 steps. First, we'll build the necessary Docker image. So this will be a single image that we will use for both the job cluster service pod and for the task manager pods. It's going to have exactly the same stuff in it in both cases. We will then set up the job cluster as a Kubernetes job and a set of task managers as a Kubernetes deployment. Then we'll set up a job cluster service wrapped around the job cluster. And finally, we'll add Minio for doing checkpointing. So first of all, how do we build the Docker image? So you describe a Docker image by writing a Docker file. And I've just shown a few key parts of that Docker file here so I can talk about them. So you can see here at the top that the Docker file includes a complete Flink distribution. It also includes the jar for your application. So we're building a job-specific Docker file here that's going to contain your job, a specific version of Flink, and also the configuration files that you want to have for that cluster for this specific job. So you're going to have the Flink conf YAML file, the logging properties, and a shell script for booting the image. That shell script looks like this. So this is the key part that lets this same image work as both the task manager or as the job manager. So you can see that happening here. There's an argument passed to this when it starts that indicates which of these 2 roles a specific pod is going to play. And you can see then on this next slide that we have the manifests. So these are the Kubernetes manifests. On the left, you see the manifest for the task managers, and on the right for the job manager. And in the green, you can see where it says task manager or job cluster. These are the arguments that are supplied, indicating what role it's going to play. You can also see that we're providing the specific image that's going to be run, and it's the same image for both of these cases. Now, in the case of the job cluster job, I've chosen to make this a Kubernetes job because a Flink application needs to run until it's completed. That might mean forever, or it might not. It might be a batch job that's just going to run to completion, or it might be a streaming job that's really being used in a batch sort of way. So the job abstraction fits well. And for the task managers, we want these to run indefinitely, and we want to have a scalable fleet of them. So again, the deployment abstraction, Kubernetes, is a good fit. And I've made the number of replicas parameterizable with an environment variable just for convenience. Okay, the next step I just want to talk about briefly. In both cases, I've set the image pull policy to never. This is something I did for convenience and development. This means that Kubernetes is never going to reach out to Docker Hub or some online repository to get the image that's been specified. It's just going to look for it locally. That's what I wanted while I was in development, but I wouldn't put this in to something I was going to use in production. And finally, you can see here that I've also injected the job manager RPC address. I want to talk about that for just a second. This is something that I could have put into the configuration file, but I've chosen to inject it as the thing is started up in this way because I wanted to have a Flink configuration file. Remember, that file gets built into the Docker image, and I wanted to be able to use that Docker image in a number of different contexts. So here I'm using it with Kubernetes, but I can also use it that image to run with Docker Compose, for example, when a different RPC address will need to be used. So that's why I've made this something that's passed in here. And what that is the, you can see it as the name of the job cluster job. But what it really is, we're going to see it later as the name of the service. So far we've established this much of our desired infrastructure. We have our task manager deployment, and we have this job cluster job. Now, as the next step, we're going to expose that job cluster job as a service. So that's what this is doing here, this bit of YAML. This is another Kubernetes manifest, and it's describing, so it's supplying the name. So that's that routable name that you saw in the previous manifests as the DNS name for this service. So this is where the name comes from. We can, and we can see the ports here in green that are being exposed internally within the cluster for using this service. And then we can also see the ports in blue that are being exposed externally. So that gives us this additional piece of infrastructure now that wraps around the job cluster pod and makes it a service we can use. So finally, to have a more complete example to talk about, I wanted to set up Minio and be able to use that for checkpointing and save pointing. So Minio is an open source S3 compatible storage service. It's lightweight, it's easy to set up. It seemed like a good fit. And there's several components needed to set this up. So first of all, I need to have a persistent volume claim. So in this case, I've said I want to have 10 gigabytes of read-write storage. And since I'm running this standalone, I'm just going to have one instance of this. I'm not going to have a fault-tolerant cluster, Minio cluster on my laptop. I'm just going to have a single instance. Then I want to set up a deployment to serve this up. I'm not going to talk through this in a great detail, but I wanted to point out that the access credentials are sitting here, so we have the key and the secret. That'll need to match up with what things we're doing later as well. Then here we wrap this in a service. I'm giving the service a name, and that name and port need to match what I'm going to use in the flink.conf.yaml file. So when I set up my Flink configuration, the S3 endpoint needs to match what I'm putting in the description of the Minio service. And then I also have a sort of a sidecar job that's just setting up the Minio buckets that I'm going to use. So I'm going to have this state bucket. So that someone needs to create that. So I put that in there. And you can see here in the Flink configuration, again, I'm specifying now that my checkpointing and save pointing, I want to go into this state bucket that got created above, and providing, again, the necessary secrets. Now I've included this because this is stuff I wish I'd done when I'd started down trying to implement this. So there's two ways to specify buckets in S3 file systems. You can do it in virtual hosted style, as you see above, where it says state.minio service, port 9000. So there it's dynamically creating a virtual host name that can be used to address the bucket. I found getting that to work in Kubernetes more trouble than it was worth, and it was much simpler to use the path style naming you see there, where it's minio service /state. So while that's much easier to get working in Kubernetes, it turns out that getting Flink to use that style of addressing is a bit challenging. There is a configuration parameter called s3.pathstyleAccess that you can set to true, but only if you're running Flink 1.8 or newer, meaning it's only just about there since Flink 1.8 hasn't quite been released yet. So this example is running on Flink 1.8 release candidate 2. The other option would be to specify the endpoint with its IP address rather than a host name, because if you haven't provided a host name, then it's unable to prepend the bucket name to the host name. So you can force it to do path style addressing in that way if you'd rather. So that finally gets us to this point where we've established the complete infrastructure that wanted to have for this job. So let's watch this run for a minute here. So first what I'm going to do, so this is stuff you can do if you clone the repository. So first you can make the jar for this job. And that's just using Maven to build the application-specific jar. That's been successful. So now what we're going to do is build the Docker image. And here I've chosen to do it from a local copy I have of the Flink tarball. So that's building the image, putting in all the pieces we talked about. And now in this repository I'm sharing with you, there are several different ways available to run it. In this case, I'm going to run it with Kubernetes. So I've moved into the Kubernetes directory and typed make run to start up everything. And now that everything is there, I can go ahead and look at what's there using kube control. So here you can see all the different services and pods and so on that have been built. And I'm going to look at one of them. So I'm picking this task manager pod, and I'm going to just look at the logs. And here you can see the job running again, just as we saw before, where it's printing out the user IDs and the event counter for each of those. Now, it's easy enough if you want to go ahead and rescale this, but keeping in mind that we can't really do that in a super dynamic way. So what you have to do is first use kube control to scale the deployment. So here I'm telling Kubernetes that I want to have 2 task managers instead of 1, so the one that was there before. And now that I have 2 task managers, I can scale the parallelism of the job up to 8 because I've configured each task manager to have 4 slots. So if you want to scale up your job, you have to do it in this 2-step approach of first making additional resources available and then telling Flink to run in a way that's going to consume those resources. A few tips about debugging this sort of, let me check on questions before I move on to the next section. Okay, I think we're good with, so there's a question here about job cluster versus session cluster. So I chose to make this example about the job cluster approach because I think it's the more interesting approach. It fits better into what we sometimes call Flink as a library, where you become more focused on developing your application and you're thinking less about, oh, I have to stand up this cluster that's going to run forever and provide resources to many, many jobs. It makes sense to have a session cluster in cases where you're going to have many very short-lived jobs. For example, if you're going to be submitting exploratory SQL queries as short-lived jobs, that's a great way to go. But for applications that you're developing to run indefinitely, I think the job cluster approach is nice. Let's see. Do I recommend not defining the parallelism in the configuration? Well, given the way that Kubernetes works at the moment, since you're not going to be able to adjust it super dynamically, I don't feel like it makes a big difference at the moment where you sort of statically build in the parallelism. You could define it in the application itself or in the Flink configuration file, but I like to bind it as late as possible in general. Let's see. No, someone asked if I've tried running this in AWS. No, I haven't done that yet. I look forward to doing that soon, but haven't done it yet. Someone else asks if the application jar is copied inside the Docker image when the Docker build happens. Yes, that is exactly what happens. So in that way, the Docker image becomes application specific. I don't have an example like this for building a session cluster. No, I don't. In some ways, that's enough different. It's really, I think, would require a somewhat different approach. All right, I think I'll shift gears now and talk about debugging for a few minutes. I showed you this file earlier. This is the Docker entry point script. And I've highlighted a couple of lines here. So I find this super helpful. What this does is that greps through the, it filters out the comments in your configuration file and puts the resulting important bits into the log file. So the result is this. In the job cluster log file and in the task manager log file, you end up with a very straightforward summary of the configuration that you're running with. And I found this really helpful when I was debugging things, because I could look at this and go, oh, that isn't what I expected. Oh, that's right, I forgot to rebuild the image, for example. It's just kind of kept me from making stupid mistakes. Another thing that I found pretty helpful is that you can log into these machines. So here I'm going to just show an example of logging into one of the task manager machines. So I'm just grabbing the routable name of the machine and asking for a bash shell on it. And then you can do all sorts of things. One of the things I found myself doing was just checking to see that the DNS name of the job cluster service was routable from each of the task managers. I was having some network problems at one point, and this was certainly helpful. All right, now I want to just talk a bit about our future plans for where this is all going as the community goes forward. So there's, of course, great interest in having tighter integration between Flink and Kubernetes. And this is being approached in two different ways. And we call these active mode and reactive mode. So what I mean by active mode is that Flink would be aware of Kubernetes and interact with it directly, in much the way that Flink currently interacts with Yarn. The other style is where Flink is oblivious to its environment and reacts to resources as they become available. So in reactive mode, if more task slots come into existence, Flink would then just react to that and start using them. So here you can see this active mode. So what would happen here is that you would begin by submitting a manifest describing the active mode deployment you want to have, and the already existing Kubernetes deployment controller would see that and start up this application master in this mode, start up this pod. That pod would then expose a service to which you could submit your job. When you submit the job, the mini dispatcher in the application master would start up a job manager. That job manager would request slots from the resource manager. The resource manager would react to that by using the deployment controller to create whatever resources need to be created. So it would spin up task managers. Those task managers would register their existence with the resource manager, which would then request slots from them, and those slots would be offered to the job manager. There's a ticket on Jira that's tracking the work on this active mode. So this is Flink 9953, and you can see that much of the work to do this is currently in progress. The other approach to thinking about this is what we call reactive container mode. So this would then rely on external systems to start and destroy task managers. So any one of the, something like Kubernetes horizontal pod autoscaler, or the Google Cloud autoscaling, or the AWS autoscaling group, any of those have mechanisms to describe the kind of scaling behavior you want to have. And we would rely on those mechanisms to scale up and down the task manager deployment. And Flink would just react to the disappearance or appearance of new resources and, and run accordingly. Now, by definition, the changes in Flink that will support this will work with all cluster managers. So this is not a Kubernetes specific feature that's being worked on. This is being done under the umbrella of Flink 10407. And as you can see, this has been designed in great detail, broken out into stories, but for the most part isn't being actively worked on yet. So to sum all this up, Flink currently supports job and session clusters. I've really only shown you how to do job clusters in detail in this talk, but if there's enough interest in session clusters, maybe we can look at that at some point in the future. I've shared with you an example. This example can be used with Docker Compose, with Docker Stacks, and with Kubernetes. So it's a nice sort of multi-purpose example of different container infrastructures, well, that all share a fair bit in common. We've talked about active and reactive container modes and how that's work in progress. And if you're interested in these topics, please join in the discussions going on the dev mailing list for Flink. So thank you very much. And let me see if there are more questions at this point. So I'm asked if I'm suggesting Minio for production use. That depends. I think if you're running on AWS, why wouldn't you just use S3? The same kind of story goes for any of the major cloud providers. But yes, in some cases, I think Minio could make perfectly good sense for production use. Best practice for monitoring and logging. My first inclination would be to say use Prometheus. And if I have time at some point, I think I'll add that to this example, but haven't done it yet. There's a question about restarting a cluster with a save point. So you would do that you would do that from outside the cluster. So you would use the cluster REST endpoint or the CLI to do this. So just make sure the save point goes somewhere that you can refer to externally. Has some URI you can use to name it, and you can pass the address of the cluster in as an argument to the Flink command line. So basically, you would Flink run -s save point -m where the cluster is. Still looking over the questions here. So there's a question here about does the Flink cluster have a single configuration file, or more specifically, if we needed distinct configuration files, then would we need to have separate deployments? I don't think you'd end up needing separate deployments, although I haven't thought about this too deeply yet. But I believe you could inject just as we currently are able to inject at instantiation time, the distinction between being a task manager or a job manager, I think we could do roughly the same thing, but with environment variables and so on, to be able to differentiate things more dynamically. Is S3 the recommended platform for supporting snapshots? Well, what's recommended is to use some sort of distributed file system. You definitely want some durable persistent storage here. So that could be S3, that could be HDFS, that could be NFS, could be any one of the S3 compatible file systems like Minio or Ceph or whatever makes sense. Any limitation on the number of task managers? Just whatever, whatever physical resources you have available, that's what's going to limit the number. But no, we see clusters with enormous numbers of task managers. Any suggestions on liveness probes for task managers? I don't think that's really necessary. The way that Flink works is there's already keep alives going on within the cluster between the job manager and the task managers. And the job manager is really already taking care of that. It will detect if the task managers go away. So there's already, I guess, a Flink specific solution here. So there's currently no need perceived to do this in a cluster specific way, or cluster framework specific way, I mean. Is using Yarn the recommended setup for the future? No, I wouldn't say so. Yarn is fine, but I think that these containerized environments like Kubernetes are a great way to go as well. Could a Minio target be appropriate for a safe point? Yes, absolutely. I've experimented with that myself. It's worked just fine. Are there latency requirements for the checkpointing storage? Not so much. The checkpoints are being written asynchronously, and so it's pretty tolerable for that to take some time to complete. I mean, obviously you're not comfortable if it's going to take forever, but you don't have strong latency requirements, no. Any suggestions for sizing the JVM heap and request limits in Kubernetes? I guess I don't see this as a Kubernetes specific question. I don't think there's anything particularly special here. It is important that you size the heap to be large enough so that the framework isn't going to kill your job for exceeding the process size limits. But that's kind of a larger topic to try to cover. I'm not going to be able to answer in depth here. I'm asked where you can find the slides. I'll have to figure that out. I'm sorry, I don't have an answer for that right at the moment. Is there a recommended minimum period for the checkpoint? Interesting question. So the checkpoint interval should be whatever makes sense in terms of your comfort zone, in terms of how long you're willing to wait for recovery to take. So if you think about it this way, if you've got some job that's processing live data and you set the checkpointing interval to be every 10 minutes, then in the worst case, you're going to have at least 10 minutes of data to replay after the job has been restored before you can catch back up to processing live data. So depending on your SLAs with whoever's, whatever your guarantees are that you supplied to the folks, depending on your job, that may be uncomfortable. Now with jobs with very large amounts of state, like terabytes of state, frequent checkpointing has in the past seemed like something that could take a very long time, but with incremental checkpointing these days, it's pretty practical to have fairly frequent checkpoints even when you have very large amounts of state. All right, I think the questions have died down. I'm sorry if I didn't get to all of your questions. In some cases, I don't know the answers, but I will be learning more and sharing more as I learn more in the future. So thank you very much for joining us, and I'm going to wrap this up now. Go out and have a great day. Bye.